topic last time? Oracle machines, right? And Oracle machines are very important. So these definitely are right. I'm well aware that the picture I sketched of Oracle machines is not necessarily the most precise mathematical definition you've seen, but I think it's precise enough, and you should make sure that you understand what's going on. And we'll use it quite enough that if you don't understand it, you will be brutally confronted with that fact at one point or another. So I guess you don't have to worry about it too much. Okay, but then the other thing that I skipped near the end of last lecture because we were running out of time is this idea related to the Church-Turing thesis, which says that anything which is effectively calculable in one way or another, right? The so-called the intuitive notion of being effectively calculable, or the intuitive notion of computable, corresponds to the notion we defined of being Turing machine computable. And so the book provides a little bit of evidence for this, because he gives essentially two definitions. The one is through Turing machines, and the other is through Gödel's mu recursive functions. And so part of Church-Turing thesis is that this class of functions defined by this handful of functions is in there, and it's closed under these operations, that this class of function exactly corresponds to our notion of Turing machine computability. And I promised I would give you a extraordinarily brief view of yet another notion of computability, which I hope will look sufficiently different that you are unlikely to believe necessarily that it's the same one, but it is the same one, and I'm not going to prove it, because these proving equivalences between notions of computability is what's the right description to give? It is usually not hard, but boring and unpleasant. And so you don't want to do this. What you really want for these kind of things is you want somebody else to have done it, written it down in a nice way, and then you glance it over quickly and see whether what he's done confuses you. Convinces you. I guess if it confuses you, then you still have some work to do. If it convinces you, then you're all good. Okay, what is this very different looking notion? This is the lambda calculus, and the lambda calculus is something which in the math department is usually not very much looked at, but in computer science department it's a very nice notion, because you can, right, the calculus I'll present here is the untyped lambda calculus. You can insert types in there, and then you get a nice typed language. And then on top of this, you can implement all sorts of things you might care about in computer science. You can implement some exceptions in a very nice way and study how exceptions work. And then you can add all sorts of other data types to this and figure out how these things interact with each other. And so, but in math departments, you don't see this necessarily very much. So. What does the lambda calculus consist of? The lambda calculus consists of a collection of lambda terms, and a rule to compute with lambda terms. So first I'll define what the set is. The set lambda consists of some set of variables. Take your favorite countable set of variables. And then it has two closure conditions. One says that if you have two lambda terms, then multiplying them together, or maybe more accurately, concatenating them gives you again a lambda term. And the last rule says, if you have a lambda term, then you can form lambda x dot that term, which is the abstraction. Or that's how you want to think about it. So what is this set of things? It consists of a bunch of variables. You can concatenate things, and you can do this funny operation with it. So in there are things like lambda x dot x. In there is something like lambda x dot lambda y dot x times y. Right? These are all things which you can form by applying these rules some finite number of times, and then you can build up with it. Now this is a common notation also used informally, where you would, this is not in the lambda calculus, but it's sort of the informal version. Lambda x plus 1, right? There's no addition in my lambda calculus yet, and so this is the informal way to think about, or the informal way the lambda notation is often used. I think of the expression x plus 1 as a function of x, and to emphasize that it's a function of x, I write lambda x dot x plus 1. The lambda indicates what the input variable is. And I can also do something like this, lambda y dot x plus 1, right? This is also a function. It's a function of y, and it's a constant function that always equals x plus 1. And if you happen to know what x is, you could compute it. If you don't know what x is, you can't compute it. And so this is the informal use of the lambda notation, which is common. You see this a lot. It's inspired by the formal use. Okay, so now there's two rules to consider. Rule number 1 is called alpha conversion. An alpha conversion corresponds to something which you all know already. The name of a bound variable doesn't matter, right? The integral from 0 to 1 of x dx is the same as the integral from 0 to 1 of y dy. Right? The x dx and the y dy, this is the bound variable. Its name doesn't matter. The same is true in the lambda calculus. If I have lambda x dot some expression involving x, maybe x appears multiple times, then I consider this equivalent to lambda y dot y. And there is some side conditions you have to be a little bit careful with when you do this kind of thing, because right, maybe y is a bound variable in here somewhere, and then you get some clashes. So alpha conversion is exactly what you intuitively think as the names of bound variables don't matter, as long as you don't do anything silly. Right? I'm not doing anything very careful and formal anyway, so I feel don't do anything silly is an appropriate instruction at this level of detail. And then there is the big notion. Beta conversion is the engine of the whole thing. Beta conversion is the thing that makes these formal lambdas mean kind of what the informal lambdas mean. And that is that if you have any lambda term in which a so-called beta redux appears, if you have something lambda x dot n applied to n, so you have an application between two terms, and the first one of this is one of these lambda terms, then this beta reduces to m where n is substituted in for the x, right? And so this is my rule of alpha conversion is bookkeeping. If you don't do bookkeeping, then silly things go wrong. Beta conversion is where real computation happens.
When you say an application, is that the same thing as concatenation?
Yes. The result of this, where the first term was one like that. Exactly. You think of this as an application, even though formally it's maybe a concatenation. But I'm so far from formal in this description that I really don't care too much about making the distinction. So, and my claim now is that I have just given you a perfectly reasonable notion of computation. What is the notion of computation? Well, here is one computation step. And so now I could have formulated a different Church-Turing thesis, and that would be a Church-Turing thesis which says anything is effectively computable if you can write down a lambda term such that if you apply this step repeatedly, you compute the function you're trying to compute. Now that's very fuzzy. So I should give you one example to show you that this is not completely ridiculous, which I think if you see this for the first time, thinking it's completely ridiculous is perfectly reasonable at this point. But I'll give you one example to convince you, and then if you care about this stuff, you'll have to twist my arm into giving some seminars about it, and I'll be happy to. But yeah. Okay, so what is the one thing we actually wrote a Turing machine for? That was addition. Right? So it would be reasonable now for me to say, if this really corresponds to a notion of computation, then I should be able to write down a lambda term corresponding to addition. And now you notice, and this is why this is so nice, that now it becomes even less clear what it would mean to write down a lambda term that corresponds to addition. With Turing machines, at least we had numbers on the tape. Admittedly, there were only zeros and ones, so there weren't a lot of numbers. But here, there's they're not even apparently there. Before there were at least zeros and ones, and then you can think maybe we do binary. Before I said anything about how we were going to talk about input and output, you could have some guesses. I now guess that you don't have a guess about what it would look like, but this is obviously a guess. So I'm going to have to do two things in order to show you that this is not an utterly ridiculous notion. I need to show you that you can come up with terms which reasonably can be said to represent natural numbers, and then I need to come up with a lambda term which does addition. Right? That's a far cry from showing that this is the same as Turing machines, but it's a first step, and I don't have the time or energy to do any more than that. So, step number one. Church numerals. I need to come up with lambda terms which represent natural numbers, and of course, just like for Turing machines, this is going to be a convention. There's going to be lots of choices which in reality you could take, but I'll take one which maybe by the fact that I wrote Church's name on there is not very original. It's convenient and it works pretty quickly, and I'll copy it over from here just to make sure I don't put things in the wrong order. So I'm going to write n bar for the numeral corresponding to the number n. So this should be a lambda term of some form. The lambda term I choose is lambda f dot lambda x dot f to the power n x. Right? F to the power n is clearly an abbreviation for f n times, right? Because my abstract syntax here does not involve exponentiation, but I suspect that if I hadn't said anything, you would have still guessed that it means what it means. And commonly, I should also put this in. Commonly, we write lambda fx dot fn to the x. Right? We contract our different lambdas together, and you can see which the input variables are by looking where the dot appears. It's a convenient abbreviation that makes our life ever so slightly less miserable, and if you can make it less miserable, it's always good. So now what we want, well, I hope I've made you want this now. What we want is to come up with a lambda term, let's call it add, such that if I apply add to the term for n and then to the term for m, this reduces in some number of steps, that's what the star means, in some number of steps using just beta reduction, maybe some alpha conversions along the way, just beta reduction to the term corresponding to n plus m. Right? If I can come up with a lambda term add like this, then I've shown that addition can be represented in this lambda calculus. And that's a good start. Maybe I should put parentheses around it. It doesn't really matter. Everybody happy that this is something which I've argued is at least a little bit desirable? Right? Maybe I should leave it as an exercise. I'll give it. And is the lambda term lambda n dot lambda m dot lambda f dot lambda x dot n f m f x. And so this is always a good thing to do. I've used the variable n for what's going to correspond to my input, the numeral n, and the variable m for what's going to correspond to my numeral m. This is it. How do you see this is it? Well, now you have to compute it. Add of n m is equal to, right? If I do two lambda reductions, then the first one replaces this n in the expression everywhere by n bar. The second one replaces this m in the whole expression everywhere by m bar. So this reduces in two beta steps to lambda f dot lambda x, which I'd already promised I would abbreviate to lambda fx dot n bar f n bar fx. Right, I've just done the so-called beta reduction with the first two variables. Did I get it right? And at least it doesn't look like we failed already, because the term should be lambda fx f to the n plus 1. Well, at least we have, right, two binding variables here, so that works. And here you also notice some importance of this alpha conversion, because n bar is of course lambda fx fn x, and this f here in n bar is not the same f as this f. Right? These are bound variables, and by alpha conversion I can pretend that the one that occurs in n is different from this one. if you don't pretend that, then you made one of these things which I called stupid mistakes, silly mistakes a moment ago. If your bound variables would clash. Okay. So now what does this go to? Lambda fx dot. And now I have here two places where reductions are going to happen. Here, because n is a lambda abstraction applied to f, and m is a lambda abstraction applied to two things, so there's some better reductions I can do. And while I'm doing this, I'll rename the bound variables, because now I'm actually going to write them down. So if I apply n to f, then I get this f goes away, and my f appears here. So this first term becomes lambda y dot f to the n y. Right? This n applies to f becomes this, and I've used alpha conversion to rename this x to y in this expression. And then I do the second expression here. The second expression is lambda fx f to the mx. And if I do two steps of lambda reduction, this corresponds to f to the mx. Right, and so I did 3 steps this time. And now we look at this expression, and this expression has exactly one more beta reduct remaining. A beta reduct is the thing where you can start doing beta reduction. There's exactly one more remaining, so this goes into lambda fx dot fn fmx. And if you have n f's followed by m f's in a row, then this is exactly the same as lambda fx dot fn plus mx, which is, as promised, m plus n bar. I guess I promised it to be n plus m bar, but the addition is mostly commutative. So at least I can do addition. Now if you look at this, then with a little bit of creativity, it's not that hard to do multiplication. Other stuff quickly becomes a lot more involved, of course. Just like Turing machines. The one for addition was reasonable. The one for multiplication can be done reasonable. I've done it. If you change the tape alphabet to be bigger, then otherwise you have to do this encoding and decoding. It becomes complicated. But very quickly, you don't want to actually do the programming of the machines anymore. You don't want to have to come up with this kind of thing. You want to say, well, by the Church-Turing thesis, if I can reasonably argue that it's computable, then it is computable. Therefore, there exists a term. And if ever you're not convinced by this argument, then it's up to you to program a Turing machine or write a lambda term or come up with a definition by recursion and minimization to show that it really is computable. As promised, I hope. Looks nothing like Turing machines. But again, it's equivalent. Any questions? Okay. Well, in that case, I'm going to leave lambda computation. Like I said, I'll be happy to give some talks on this in the seminar. It's an interesting subject. Lots of interesting stuff comes up. It's just not the subject of this class. So, what is the subject of this class is something we talked about a little bit in the first lecture. In the first lecture, I gave you something clearly labeled lie. This class is about what a computer can compute in principle. We don't care about practical concerns of space and time. And just at the end of last class, we defined what oracle machines were. And I'm not sure if I wrote down the notation, but this is sort of the common notation for saying the ETH oracle machine using on its oracle tape the set A on input X. And this, of course, it can never hold, in which case you would say, right, it never holds, or it can hold and be equal to Y. But this is the notation for the ETH oracle Turing machine on input X using oracle A computes and gives output Y. So it's a nice notation. So the first thing we can now define from this is the notion of Turing reduction. We say for sets A and B, sets of natural numbers, we're almost exclusively concerned with like functions from naturals to naturals, sets of natural numbers, these kind of things, because everything else you might want to care about you can encode into natural numbers, and so nothing too new happens. We now say that A Turing reduces to B, if and only if. So before saying what the actual definition is, the intuition here is supposed to be that A is in some sense simpler than B. Or this is a B. Or another very good way of viewing this is if you were to somehow have access for a procedure of deciding membership for B, then from this you should be able to get a procedure for deciding membership of A. Now for many sets you couldn't possibly get a decision procedure in any effective sense because many sets are too complicated, but that's a good intuition for this, that deciding membership in A is easier than deciding membership in B. And what should this now mean? Well, this should mean that there exists a Turing machine program for an oracle Turing machine such that the characteristic function of A is computed by the ETH Turing machine which uses oracle B. And so the characteristic function is exactly the function that says that the characteristic function of n is equal to 1 if n is in A and 0 if n is not in A. And so this exactly says, this equation, that this ETH Turing machine, or this ETH oracle Turing machine, if it gets to ask arbitrary questions about membership in B, can decide membership in A. And so this is key definition number 2. I guess number 1 was the oracle machines, number 2, Turing reduction. This is as basic as it gets. Questions on that?
What would the definition be if you wanted to put it in terms of lambda calculus instead of?
Actually these sets of natural numbers are now subsets of the lambda universe. So you have a notion of 0 and 1 in lambda terms, and so you need to find a lambda term. I've never actually seen the notion of oracle lambda term. But I guess you could just add to your language terms of the form n is in B or n is not in B, that according to right, this wouldn't be beta reduction anymore, but this is then some other reduction which goes to 0 or 1 depending on membership in B. I guess that is a reasonable way to make oracle lambda terms. And then, right, as soon as you have this notion of oracle in your lambda calculus, then this same statement makes sense. There exists a term in the oracle lambda calculus which always computes equal to the characteristic function. I've never seen it, but this is what makes sense to me here and now. And I suspect it will still make sense to me when I'm back in my office in a little bit. If it doesn't, I will get back to it on Monday. Maybe not Monday, because not a lot of you will be here. But Wednesday.
Does this definition still have substance when you can't compute membership in either set?
Absolutely.
You still have...
Absolutely. All it says, right? What is an oracle machine? An oracle machine is a machine that can compute like an ordinary Turing machine, but it can also ask, is this number in B? And get back an answer 0 or 1. And so this is just a Turing machine which has a black box attached to it, which answers these questions. Well, you can imagine a black box for any set, computable or not. So you would like this only to make sense when A is computable?
Well, no, then of course.
Right. This is sort of a nice observation. What happens when A is computable? Oh, I didn't define computable yet. This is coming really soon. I can just define it now. I'm going to define it anyway, it might as well be now. And it might give some insight into what this definition means. So we say A is computable if and only if there exists a Turing machine program, no oracles, such that the characteristic function of A is equal to the function computed by the Turing machine. So this is saying the characteristic function of A is computable outright. There exists a Turing machine program which computes it. And so this was the first observation. What happens with computable sets in Turing reduction? Is there anything
below everything?
Below everything, right? It is the case that if A is computable, then for every B, A Turing reduces to B, because right, a Turing machine that does not use oracles is also a Turing machine using any oracle without using the oracle. Right? And now this is one of these things where of course you might say, well, that's a little fuzzy. And then I say, well, that's absolutely a little fuzzy, but according to Church's Turing thesis, I can be a little fuzzy, right? I need to have a convincing argument, and this argument convinces me, and therefore I think it's okay. If it does not convince you, you have some work to do. And you should, right? Absolutely. These sort of elementary observations, if they seem doubtful to you, you should think about them hard enough. But in my mind, a Turing machine program that does not contain ask this or that of the oracle is in particular a Turing machine program relative to any oracle. It just doesn't use the oracle. And if you can compute something without using the oracle, then you always get the same answer, no matter which oracle you're not using. Right? So what does this say? it says if you're looking at these Turing reductions, the computable sets are all the way at the bottom. And this is very interesting because, right, as I was promising, I'm now explaining what I think this course really is about. So we call A and B Turing equivalent if and only if A Turing reduces to B and B Turing reduces to A. Right? This is always, whenever you have a partial order, I guess I didn't prove it's a partial order. Exercise number 1, prove that Turing reduction is a partial order. Right? Intuitively, this should make perfect sense. That if you have, well, reducing to yourself is easy because if you try to decide membership in A, well, you get to ask arbitrary questions about membership in A. I can do it. I hope so can you. If A reduces to B and B reduces to C, then you have this Turing machine which asks B oracle questions, but using the C oracle you can always answer such questions. And that is fuzzier than I've done up to this point, but it should be at least enough of a hint, I hope, for you to be able to prove transitivity of this kind of thing. Yes. So whenever you have such a thing, then if you do this, you get a nice equivalence relation out of it.
Is partial order the right word? Because then if A was reducible to B and B was reducible to A, then they would just be equal, right? Just equivalent.
Whichever book you open, right? The one book says it includes it, the other doesn't. My mind does not include this distinction very much.
I think what I was trying to ask was, are there distinct, is it known for sure that there are different A and B that are, where A is strictly less than B in this sense, but they're both not computable?
Absolutely. This is implicitly answered by what I'm about to say.
Okay.
By what I'm about to say the course is about. If the answer to your question, I forget how you asked it, if it is either no or yes, depending on how you asked it, then the course would be trivial and nothing much would be going on. And as soon as I explain it, you can figure out whether you have the negation or I have the negation. So this is an equivalence relation. Check it. But that means that now I can define the equivalence classes. You can write it like this. It's also often written as deg sub T of A, because this is called the Turing degree of A. Right? What does the set of all sets equivalent to A consist of? The set of all sets equivalent to A consists of all those sets where, in the sense we have just defined, answering the membership problem is exactly equally hard. Right? Two things are equivalent if whenever you can answer membership in A, you can answer it in B. Whenever you can answer it in B, you can answer it in A. So this gives you a nice equivalence class. And then here we have the structure. Oh, one more definition. Standard definition, but 1 second. The Turing class is Turing less than or equal to the Turing class of B, if and only if A Turing reduces to B, and if it's not clear to you, then you better check that this does not depend on representatives, because otherwise it would be a bad definition. Question?
Yeah, you said something about the equivalence classes, if they have the same, I guess, Turing degree as we call it, and they're equally hard.
Yes.
Computing it. What do you mean by hard? That is to say, like, can an infinite class and a finite class have the same level of difficulty?
A set.
I mean, sorry, set.
Set.
Yeah,
An infinite set and a finite set? Absolutely.
yeah. Okay.
Why? Computable set. Look at the computable set. So if I give you a finite set, then it's computable.
Mm-hmm.
right? Because how do you compute a finite set? Well, again, I'm going to do this in a nice hand wave, but this is again one of these, I think, very convincing hand waves. If you give me a finite set and you wonder, is this computable? And I say yes, because my Turing machine contains a table of all the numbers in this finite set, and given an input, it just checks whether it is in the table. If it finds it in the table, then it says yes. If it does not find it in the table, it says no. So finite sets are computable. But so is multiplication. It better be. I did not give you the Turing machine. I've done it before. You should be able to do it with like 30 instructions if you take a little bit larger alphabet on the tape. So multiplication is computable. Therefore, you can search for, if you give me a number, I can multiply by 2, and so I can check whether a number is even. You give me the number, and I check for all numbers less than that number, whether twice that number is equal to the given one.
No, I mean, I agree that
So this set of all even numbers is computable, and computable sets are equivalent. So we have a finite set that's equivalent.
So hard is just tied up in computability.
Hard is tied up in computability, okay. And really, of course, I was completely cheating, because when I say two things are equally hard, I mean they have the same Turing degree, really, right? That would be the formal definition of equally hard, but because these definitions, according to George Turing, correspond to some nice intuitive notion, I say intuitive things like that sometimes. Okay. But really the definition would be the Turing degrees are the same.
I just wasn't sure if you meant, number of steps or something like that.
No. No, these can differ wildly. Right? The finite set, the infinite set, can be very complicated things going on. The set of primes is computable. Well, deciding if something is a prime is clearly harder than deciding if it's even. Partial order on the Turing degrees. So here comes the step we care about. The collection of all Turing degrees under this partial order. This is the structure of the Turing degrees, and a big motivating question for this course, which I think in some sense this question plus related stuff is really what this course is about, is what does this structure look like? And so your question is yes or no, because if it was either yes or no, then this would be trivial and not very interesting to study. Although it might be an interesting proof, but it turns out this is a very non-trivial structure. There's lots of different classes and lots of interesting things going on. And we already know at least one thing about it, by our observation here about the computable sets. This structure has a minimal element, and the minimal element is the Turing degree of computable sets. All computable sets are equivalent, and all of them are reducible to any other set. So the degree of computable sets is exactly the minimal element in the structure, and then there is all this other stuff above it, where we're going to try and make some observations about.
I suppose it's known that there are incomparable elements then?
this structure?
Yes, so there are incomparable elements. We have just arrived on page 7 of my notes. The proof is on page 10 of my notes. But you already know this. I don't mean you, I think all of you already secretly know this. Because if you've been in the mathematical community for a while, I hope at some point or other you've heard of the halting problem. And the halting problem is sort of the standard example of a non-computable set. And something which is not computable is not equivalent to something which is computable. This is a nice quick exercise, I think. If you understand the intuition of Turing reduction, you'll notice that if A Turing reduces to B and B is computable, then A is computable. Right? Because here's the proof again, nice hand wave. If I'm trying to decide membership in A, well, I know A Turing reduces to B, so I can decide membership in A if I get to ask oracle questions of B. But B is computable, so I don't need an oracle to tell me whether something is in B or not. I have a Turing machine which does it for me. And so if you stick this Turing machine in the right way in the original oracle Turing machine to answer your questions, then you have an outright computation of A. I.e., anything which Turing reduces to something computable is computable.
Is that the same thing as just saying that that's a minimal element?
Pardon?
Is that the same thing as just observing that that's a minimal element?
Yeah, I guess it's the same proof essentially, yes. But I already proved that. Did I give the same proof just now?
Right.
Did it actually answer your question? I forgot your question halfway along.
It's known it's not a linear order.
Oh no. So this, of course, is one of the questions. Are there incomparable elements in here? It's a nice question. No, it's absolutely known. There's an awful unknown about this structure, and so the trick is going to be that we need to start knowing this as well. But then you'll notice that we're going to prove that fact, depending on how far we get in the book, 2 or 3 times, because to show that that incomparable elements exist requires a couple of not too hard observations. So you want to think of this structure maybe as here's the minimal element, the computable things. Then I told you, but I didn't prove yet. Somewhere here is the halting problem. Right? It's different, but we don't know much else about it. Well, we know it's bigger then, right? If it's different, then it's bigger because that was minimal. And now you can say, okay, we're going to construct incomparable elements, and then you find something like way out there incomparable, and that'll be our first proof. I don't remember how way out there it is. You can analyze the proof and figure out how out there it is, but then. There are some, inside of this whole structure, you have like different classes of sets, and some of these sets are nicer than other ones. So as soon as you show there are incomparable elements, you wonder, are there incomparable elements that I like better than these random things up there? And then at some point, we'll start thinking about what happens here. The answer there is also yes. There are. Yes.
Are there infinite ascending chains?
Yes. How do you get that? So we have the computable sets. Then there is the halting problem of the computable sets. Is the halting problem. Then there is the halting problem of the sets computable relative to the halting problem, which is the jump of the halting problem. Then there is a uniform procedure for getting jumps, and so you have this infinite chain. Not just infinite chains exist. I would argue that this is an example of a natural infinite chain. Just holding a sequence of holding problems. That's not. As soon as you care about Turing machines, caring about holding them is a reasonable question. So that's another thing. And that's often the problem, right? You can construct these sets, but do there exist sets that do this that you might ever care about? I will show that they exist in a nice class, but are they really natural? Is